In your previous physics course, you should have learned about different forms of energy. Let me give you an example. Suppose you take a block, this red block here, and I were to lift it up a certain vertical height and place it on top of this table. Well, as I raise the block, it gains some gravitational potential energy. Now, if I were to release the block, give it a little push off the table, like what's shown in this animation, then we would see that as the block falls, it would lose gravitational potential energy and gain kinetic energy. But as soon as it hits the floor, it then loses all of its kinetic energy. Where did that energy go? Well, the block and the ground got a little bit warmer, so we can conclude that there was a gain of some thermal energy. In this video, I would like to dive a bit deeper into the meaning of this thermal energy, and also internal energy and heat. First, let's revisit a few things that you should have learned in your previous physics course. The basic energy model. So hopefully you were introduced to the idea that we have a system, and then everything outside of the system is called the surroundings or the environment. Now, a system can be considered simply just one object like this block, or it could be a combination of several objects together. An example of a thermodynamic system would be shown in this animation produced by PHET. In here, we can pump a gas. Here, I'll pump the gas in to a box. And then this box in here, with all these gas particles inside, would be considered the system. Everything on the outside of the box would then be considered the surroundings or the environment. When we say that a system is open, we're indicating that there can be energy flow in or out of the system. If the system is closed, then no energy can flow in or out of the system. It would be as though there would be a very well-insulated layer around the system so that no energy can flow in or out. Within that system, there are certain quantities that can be changed in the system by the interactions with the surroundings. Let me go back to that animation with the gas particles in the box. For example, we could apply an external force. This little guy over here that's on the outside of the box can apply a force on the box. And if I apply a force, that's the interaction between the surroundings and then onto the system, then we can change certain characteristics with the gas. We could change the pressure, the volume, the temperature. These are the state variables. But we can also change the momentum of these particles, and we could also change their energy. When you studied work and energy last year, you should have learned work on a system is done when you apply a force, you can see shown here, over a certain displacement. And so what force multiplied by the distance multiplied by the cosine of the angle between them, but in the gas situation the angle would be 0 degrees, would result in changing the energy of the system. And you should have been introduced to the idea that a system can be characterized by its total energy, E. The total energy of the system is essentially the sum of all the different types of energy. We have kinetic energy, gravitational or elastic potential energy, we have chemical energy, and we have thermal energy. Also, there is nuclear as well. Within the system, there can be many changes of energy within one form to another form, as shown by the diagram over here. Go back to our notes. We see that the basic energy principle, which is listed right over here, states that any change within the energy of the system is equal to the work done by the surroundings on it, and then all the other energy transfers that could occur. And not all those energy transfers that could occur would be kinetic potential, and the other one that they haven't mentioned is the microscopic internal energy. We'll get into that in a second. But the main idea here is that if there's work being done on the system, then the energy of the system is going to increase. If the system is doing work on the surroundings, then the energy of the system is going to decrease. Hopefully that makes sense. We know by the conservation of energy that energy cannot be created nor destroyed. So the gain of, say, energy into a system must be equal to the loss of energy from the surroundings. A system that has an internal structure can have internal energy. And changes in the system's internal structure can result in changes in internal energy. To illustrate this idea, I've jumped ahead in your notes onto page 6. And we're going to consider a slightly different system. Not the gas particles in the box, but we're going to look at, say, two balls that are connected by a spring. Now, I've got two scenarios here. I've got two balls connected to a spring that is relaxed. It's neither stretched nor compressed. And then in the second scenario, I have two balls that are compressing a spring, and you can see this little red string around here that is holding them in place. Now, hopefully you can notice that the second case, even though they both have the same, say, translational kinetic energy, the second case actually has more energy because there's some stored energy in that spring. And so we could say that that second system has a greater internal energy because of that stored elastic energy. So what exactly is the internal energy of a system? Well, the internal energy of a system is the sum, as you can see down here on the bottom of the screen, is the sum of all the different types of energies within the internal structure. That can be rotational kinetic energy, that could be vibrational kinetic energy, that could be thermal energy, that could be chemical energy. It's a sum of all of those energies together. If we go back to our earlier system and we were to take this and start rotating it about its center of mass, then we would have that rotational kinetic energy. If we were to take each of these balls and start to cause them to push them a little bit inwards and let them oscillate back and forth, then we would have a vibrational energy. Here's an animation of a two-ball spring system that has both vibrational and rotational kinetic energy. What about that chemical energy? Well, the chemical energy is the energy that's stored within the bonds of the molecules. In a simple sense, basically, if you eat something and you're the system, then you've gained some chemical energy. So what is then thermal energy? We know that thermal energy increases if the temperature increases. We get confused a little bit with internal energy and thermal energy and what is the difference between the two of them. So let's kind of dive a bit deeper in here. You see, thermal energy is related to the random motion of the atoms and molecules. We learned earlier in a previous video that the temperature of a system increases if the average kinetic energy of the molecules or atoms increase. So we see that the temperature, measured in Kelvin, is directly proportional to the average kinetic energy. So one might conclude that if you increase the rotational energy or the vibrational energy of a system, that you're increasing the temperature. Well, not exactly. You see, the thermal energy is related to the random motions of the molecules and atoms. So merely increasing the vibrational or rotational energy of a system doesn't necessarily affect the temperature. That's a bit complicated, so maybe I'll show you by an animation. So this animation is from the PHET website. It's called States of Matter. And you can see that there's a solid sitting here, and they're jiggling around. They've got a lot of vibrational energy. Now, if I were to add or heat the substance here, you can see that their vibrational energy increases, but notice also that it's very random. So the random molecular motion that you see here is what causes that change in temperature. So as I add more and more heat, the temperature is rising, and that's because the random motion of these molecules has increased. All right, back to our notes. Another word that's often confused in science class is the word heat. Now, the problem is that the way it's used in everyday English language is not what it means when we talk about heat in a technical science sense. You see, heat is not really a noun. You don't say that an object contains heat. That's incorrect. When we talk about a system, we talk about the characteristic that it has energy, but heat is actually the transit, the movement of energy from one place to another. So that occurs because there's a temperature difference between one body and the other body. So if you have this system here in orange here that's red, has a higher temperature, and then over here they have another system that's blue, that's the lower temperature, then we'll have literally energy that will spontaneously, that means naturally, move from the hot to the cold. And that is called heat. So heat is a transfer of energy from one body to another. If the heat flows into the system, then we note that heat is positive because the energy of the system is increasing. If the heat is flowing out of the system, then we're losing energy in the system, so the heat Q is now negative. There are a variety of energy transfers that occur within a system, and that would be summarized down here on the bottom when we talk about mechanical work. We have heat, we have the transfer of actual matter, mechanical waves, electrical current coming into the system, or electromagnetic waves. So all of these types of energy transfers could occur, which would cause the energy of the system to increase or decrease. In the next chapter, we're going to dive deeper into the term of heat. We're going to look at specifically the modes of which heat transfer, that is, convection, conduction, and radiation. Okay, and that's it for this video.